And so like with the disk method, what that necessitated was that the variable of integration, right, whether you were doing a dx or dy, it required that those slices that eventually, rotated out to become the disks, um, were perpendicular to the axis of rotation. So uh, let's say that our axis of rotation is right on the x-axis for simplicity's sake, and that we have a region that I'm just going to, we're just going to take this region right here, or any arbitrary region, honestly, so that the region the region that we're revolving around the axis is this region. And, so we sort of take this, spin it out, and, around the axis until it forms this sort of like hockey puck shape, kind of. Form like, it would have flat faces, of course, but like a sort of curved edge. Not that it really matters what it ends up being shaped like, but in order for those to be disks, the way that we integrate would have to be dx, because to be disks, right, the slices that you're sort of breaking this down into are perpendicular to the axis of rotation. And so you're forced to do this dx, because, if you only know disks. The width of these little slices is, an incremental change in x. So the way that we're integrating this, or the way that we're chopping this up is with respect to x. So this is for the disk method. Now, there are situations in which, doing an integration dx would be bad, or at least not as good as some alternative. So if we take, for example, this region, and I'm not going to, it's going to be a vastly simplified version. If we take this region and try to rotate it out, it's going to make this sort of shape. This sort of weird double cone kind of thing. Actually, I guess I should. Yeah. But if we, only knowing the disk method, have to do this dx, then this actually has to be split up into two integrals. Because, as you go along the region, what the curve that, the curve that bounds the region changes. For the first, for the left half, it's this sort of upward facing line right here. So let me draw that out a little bit more. Right, so for the left half of the region, it's this one curve, whereas for the right half of the region, it appears to be this other curve. And so you can't do that with one integral. You would have to sort of split up the integral right along here. So you basically have to do one integral for the left portion and another integral for the right portion. Okay, which is not optimal, but that has to be done if all you know is the disk method, because you're going to be forced to do this dy in that case. This is really... that's fine. But if somehow it were possible to obtain the same solid with an integration dy, that would be real nice. So let's make the same region. And we're still going to rotate it out the same, around the same axis, so that it forms this shape. But we're going to imagine that we know a way to integrate this that allows us to take the slices this way. And if we do, and we do this integral dy, so again, this is disk, and as a consequence, it's dx. Okay. I mean, it's not like it doesn't just say it right there, but there's this sort of mystery way of integrating, where we can somehow take the integral dy, and if we take the integral dy, and maybe you tilt your head to the right 90 degrees, maybe you don't. You might notice that you don't have to split this one up into two integrals. There's just going to be a top, or a rightmost curve and a leftmost curve, and you're just gonna, you would just somehow take the difference between the two to get, to get these slices, and so you wouldn't have to like split it up into two separate integrals. But if you took these slices, if you were to take a slice like this, let's say there's a really thin slice that you're taking, and you just imagine that you're rotating it around an axis. And you imagine that you take this and you rotate it around an axis that's parallel to it. The shape that makes is going to be this sort of shape. A hollow tube. Just a tubular shell that's empty on the inside. And that's basically what we're going to learn today, is this sort of method. This second method of finding the volume of a solid of rotation, that once you know it, you'll be able to sort of decide whether to do a particular solid with one method or the other, if that, just in case that particular integral, just in case some particular integral lends itself better to dy or dx. Okay. Yeah. So this will require slightly less prefacing, because a lot of the principles, discussed during the when we talked about the bisque method. Okay. Don't worry about this too much. Yeah, let's just skip right to this. I mean, I can tell you where these come from, or like I can tell you sort of an easier way to envision where these come from. Uh, actually, okay, so with the disk method, let's let's imagine that we have a cone, formed through the process of revolution. Um, yeah, that's fine. Okay. Okay, so we have this cone that was formed through the process of revolution. And if we do disks, our slices are going to be perpendicular to the axis of rotation. So that what we're doing is essentially we're breaking this up into a bunch of tiny, very thin circles. The area of any one of which is pi r squared. So that the formula for integrating this way becomes pi times r squared dx. So there's sort of parallel between the pieces that you're breaking up into and the formula itself. With the shell method, what you're essentially doing is you're creating a different, you're breaking it down into a different kind of shape. You are still, I'll just draw it again. You're still breaking down a cone, or any particular given shape. But how you're breaking it down is a little different. Just very marginally different. And I know this looks similar to what I just did, but I'm going to add a small detail. These are not flat disks, but actually hollow tubes that sort of nest inside of each other. Sort of like this weird, sort of telescope, kind of. So that what you've got here is a series of hollow cylindrical shells, little rigatonis or manicotis or whatever. And maybe surprisingly not shells of the pasta, because those have a completely different shape. But those are just little paper bands or soup cans with the bottoms cut out that you just sort of. But the area of any of these shells is going to be 2 pi r times h. And that's just because if you take, if you think about a cylinder and you only want essentially its lateral surface area, or if you imagine taking like a cylindrical paper band or something, the distance around this way is 2 pi r, because that's the circumference. And this way, that's the height. So the area of this sort of, the surface area of the side of this cylinder is 2 pi r h. And that's gonna translate into the integration formula for shelves. That's right. Yeah, it's so the formula is going to be that 2 pi is going to be on the outside. It's going to be an integration sign. And I guess to reduce confusion, they use p of x instead of r. Sorry, p of y, because these slices are going to, these little slices are going to be oriented dy. For any given shape, one method is going to be dx and the other method is going to be dy. Because for disks, the slices go perpendicular to the axis of rotation, and for shells, the slices go parallel to the axis of rotation. So in all cases, one of the methods is going to be done dx, and the other will be done the opposite way, dy. Keep writing x, okay. But in each of these cases, with the disk method or the shell method, the integration formula itself comes from the geometric formula for the pieces, the shape of the pieces that you're adding up. Right, for the disk method, has to do the area of these circle, these infinitely many circles that you're breaking it up into, and for the shell method, it's got to do with the sort of the lateral surface area of a cylinder, the area of these little shells that these infinitely many shells that you're breaking it up into. And we'll get into why you might choose one over the other, later. But when you look at a particular region, ideally you would not say oh well, I think disks is easier just as a method, so I'm going to do it that way. Ideally, your thought process would be, is this easier to integrate? Is this region easier to integrate? Dx or dy? And, with this particular shape, it doesn't really matter. But there are shapes where it does. And, that's the first question you should be asking. And, you choose dx or dy. And as a consequence of whether you want to do the integral dx or dy, then you would, like it would follow which method to use. So, for example, if you had a horizontal axis of rotation like this, and you decided that it was easier to integrate the region dx, that would, it would follow that if you wanted to do a dx, that would be disks. Or if you wanted to do a dy for some reason, that would be shells. So it's so the question you want to be asking yourself is not, oh, do I like shells or do I like disks better? It's is it better to integrate the region dx or dy? That should be the first question. So as we just saw, for a horizontal axis of revolution, it's that formula that was just written, and for the vertical axis of revolution, it's just the variables swapped out for x. But you'll notice, here's the axis of revolution, here's the slice, here's the axis of revolution for a vertical axis of revolution, here's the little slice that you're taking and rotating around. In either case, it's, that part's the same. So a way to remember is to remember that shell rhymes with parallel. So if your slices are parallel to the axis of rotation, that is the shell method. I can't think of a word that means perpendicular and rhymes with disk, so you'll just have to, if shell is parallel, then that must mean disk is not. But that's, once you decide whether to do something dx or dy, and you know which way your slices are oriented, based on the way your slices are oriented and the way the axis of rotation is going, that's how you can remember, oh, that means I gotta be doing this, if I want to do this dx, I gotta be using the shell method, or if I want to do this dy, I gotta be using the shell method. If based on what variable you want to integrate with respect to, and what that means relative to the way the axis of rotation is going. So if we take a look at, on the left example of this horizontal axis of rotation, v equals 2 pi from c to d of p of y times h of y dy. Now, p of y, it's the radius of the shell. It's sort of how wide the shell is, even if it's sideways or whatever. It's it's the distance from the center to the edge. And although this might look complicated, I mean there are two functions inside that integration. The radius is generally for a dy integral, the radius is usually just y. because if you sort of look at that slice, and then, it's going to be rotating around and it's going to be making this shell. That distance is just whatever y happens to be at the time. So it's actually not super complex. If you happen to have an axis that's like, here the axis of rotation is the x-axis. But if your axis of rotation was something like something like y equals 1, like if it was y equals 1 instead of being y, it would just be like 1 minus y. And I'll send out a little note about that later. But again, it's just like, if you have a weird axis that just involves like a little extra subtraction, to where it's not just y, but like 1 minus y, or 10 minus y, or 6 minus y. Now, this curve, this h of y that describes the height of the cylindrical shell. So essentially, we're making a cylindrical shell. This would call a cylindrical shell. That's that p of y, and this is going to be h of y. So essentially, the height of this cylindrical shell. That's going to be the actual like function that describes the curve. Like that's going to be the actual, whatever function this thing is. Like that's what's going to decide the height of the shell. Is the value of this actual function. So what it usually ends up coming down to is you take the function that describes your shape, that is h of y, and you just multiply it by an extra y, is usually how it happens. And then you just integrate that, and it'll be easier to see once we actually do one. And yeah. Y equals x minus x cubed, so that's, if you factor in an x, that's 1 minus x squared. Okay, so the curve is, I guess I should probably, it's a cubic function that's sort of just, upside down. But it's formed by revolving the region bounded by this and the x-axis. So that's right here, and that's going to be this boundary. So that the enclosed region is this shape right here. So it's bounded by the x-axis, but we are rotating it about the y-axis. so that when you're done, it's going to form boy. You mean like one of those like real kolaches, not like the sort of pig in a blanket kind of kolaches? Yeah. Well, like a bundt cake, I guess, if you were somehow able to get rid of that hole in the center and just sort of.
I've tried making kolaches before, but it just tastes so freaking.
It is difficult to to convey this shape, but that's.
I feel like we got it.
Yeah. That's the best we're getting. Okay. Right, so we're rotating it around about the y-axis, and it even says that x goes from 0 to 1, so you don't even really have to find these boundaries. But if you wanted, this is clearly the origin, but this would be 1 comma 0, and I mean the equation of the y-axis is y equals 0, so what you would do is set y equals 0 equal to y equals x minus x3, and then just sort of factor until you find your x values where they intersect. And technically you would find a third number, -1, but that's clearly not what's being talked about. Okay, but we're revolving it around the y-axis, and so yeah. And so let's say that we're going to do this integration dx. So that the slices are going to go this way. And if you take slices that are sort of oriented this way, if you rotated them out, they would form a series of shells. Or you could say, if you take the slices this way, that's parallel to the axis of rotation. And you do want to do this, dx, because if you sort of, if you tilt your head to the right, if you were to do that dy with the slices going like that, yeah, that'd be like the top, that'd be like the right part of this region minus like the left, the other. You would have to take one thing and subtract another, and it'd be really weird to get this to be a function of y. And in some ways, dx is just easier to look at anyways. But these would be shells, right? If we're doing this dx. So that's an example of like, the question, the sort of decision tree or thought process, this easier dx or dy. If it were easier dx, it follows then that that's shells, since those slices will be parallel to the axis of rotation. And if it was di, that would be disk. And turns out the answer is, it's easier to do a dx, so that as a consequence we use shells. Not because shells are easier or not easier or anything like that, but because to integrate a dx is easier. So v is 2 pi from a to b of p of x times h of x dx. So 2 pi times the integral of, from your x values that are your bounds are x equals 0 and x equals 1. P of x, since the x is just the y-axis, what describes the radius of each of these shells is literally just x, right? Just how far you are out on the x-axis is the radius is what's going to be the radius of your shell. So this is just x. Now the height of your shell is also pretty simple. It is just this function. It is this function x minus x cubed. And this turns out just to be a polynomial integral once you actually have it all multiplied out, of course. So simplifying that a bit further, that's 2 pi times the integral from 0 to 1 of x squared minus x to the 4th. Yeah. So the radius is often your variable of integration, and the height is usually just the curves that bound the shape. So if we were to integrate this, that's 2 pi on the outside. X squared would integrate into x cubed over 3, and x to the 4th would integrate into x to the 5th over 5. Okay. And there's no dx, there's no integral sign, there is an evaluation bar. So that when you plug these in, what you're going to get is 2 pi times, I guess, 1/3 minus 1/5. I mean, I'm just going to skip the part where I pretend not to know what 1 cubed and 1 to the 5th are. Minus 2 pi times what is ultimately 0. 1/3 minus 1/5. 1/3 is, if you want to subtract fractions, get them over the least common denominator. 1/3 is 5/15. 1/5 is 3/15. 5/15 minus 3/15 is 2/15. So 2 pi times 2/15, which is just 4/15 pi. Which, I don't know, probably around 1. It's like a little less than like 1/3 of pi, so it's probably, a valid, like 1 cubic unit. Yeah. Yeah, so in some ways, the disk method is easier, because it's a little easier to remember just what all the parts mean. But at the same time, like, it does require you to square a function. whereas the shell method does not require you to square anything. At most, it just requires you to multiply something by a linear, just an x. So they each have their benefits and their downsides. Let's see. And as it turns out, it would actually be impossible to get y equals x minus x cubed into it would be impossible to change that into x equals a function of y, because you couldn't move that around to get x by itself in any meaningful way. And even if you just sort of look at that function sideways, you can sort of see that it would fail the vertical line test if you were to look at it sideways. So this would actually be impossible to do dy, and impossible to do, and therefore impossible to do with the disk method. What's up?
So you got looking at in brackets x times x minus x is there.
Yes.
Second equation.
Right.
Where did you get the x from the px?
Oh, okay, so, I thought I made it like a mistake or something. Okay, so each of these slices is going to make a shell, right? It's going to do, oh God, there's no clean way to, well, I'm sure there is, I just don't. If we take a representative shell, it's going to form a shell like that. The radius of that shell, the distance of it from the distance of the edge from the center, is literally just the value of x that you happen to be at the time. So x is going from 0 to 1. So when it's at 0, the radius of the shell that spins out will be 0. And as I travel from 0 to 1, my radiuses are going to get bigger and bigger until my radius, finally, at the end of the shape, is a radius of 1. So, in that sense, the radius is just the x value that you happen to be at as you go from 0 to 1. And it's kind of just going to be like that all the time. There is a slight difference if the axis happens to be like somewhere else. But it's always going to be, it's never going to be more complicated than like x or 2 minus x or 3 minus x. It's always just going to be, maybe there's a constant in there, maybe you're subtracting, but it's always just going to be the variable you're using. Like the radius will never be anything like x squared or square root of x or x cubed or anything like that. Yeah. Right. Okay. And as we finish this up, we'll take a break and let's see, 1:35. 1:35. Yeah. We'll take this will take 5 minutes, and then we'll take a 10-minute break, and then for 5 minutes we'll do some shell method problems. Okay. All right. This is a lot of words, but shell parallel. So if you've got a got a vertical axis of revolution and you're taking vertical slices, that's shell. If you got a horizontal axis of revolution and you're taking horizontal slices, which would be dy, that's shell. If it's the other way around, to where it's perpendicular, that's disk. Okay. So let's look at that shape from the last section, where we were sort of forced to use the disk method because that was all we knew at the time. And it turned out to really suck because you had to split the shape up into a top section and a bottom section. And it was dy. Alright, so without getting too carried away, I suppose, I'll draw the shape. Y equals x squared plus 1 is the parabola shifted up by 1. And this part, the left part doesn't matter. Y equals 0 is just the x-axis. And x equals 0 and x equals 1 are just bounds. Might as well draw them in. Okay. So that the region again is just this sort of it's going to be this sort of straight-sided bowl with a little divot in the center. We're going to take this and we're going to rotate it about the y-axis. It ends up making this dumb little shape. Now, when we saw this previously, we only knew the disk method, so we had to take our slices perpendicular to the axis of rotation, which looked like this. And for one thing, that was dy, which is, if not necessarily harder, more unusual to see. And second, because this had to be done dy, because we only knew disks, we had to split the shape up into two regions, a top region and a bottom region. Because doing this with the disk method, the outer curve and the inner curve, or the outer radius and the inner radius, is different between the bottom half and the top half. So that was a mess. I don't remember what result we got, but we should get the same result either method. Okay, so if we do the shell method, okay. So the thing to think here would be okay, doing it dy would be a nightmare, doing it dx would be a lot easier, because then, there's just literally the one curve that you have to think of, the top one. Since the bottom curve is just the x-axis. And as a consequence, that will be the shell method, right? As a consequence of preferring to do this dx. Okay. So with the vertical, right, because these slices are parallel to the axis of rotation. So again, v equals 2 pi times the integral from a to b of the radius times the height dx. Two pi times, and through either graphing or setting curves equal to each other, you can find that this is 0, 1. This is going to be 1, 2. This is going to be 1, 0, and this is going to be 0, 0. I mean, not all of them are going to matter, but but in terms of we're doing this dx, so in terms of the region that we're integrating this from x equals 0 to x equals 1. Now the radius of these shells is, again, just going to be x. Just the value of what x is as you move from 0 to 1 is going to determine how wide your cylindrical shell is. So p of x, again, just happens to be x. The height of these cylindrical shells that are sort of formed in this way. The height of these little hollow cylindrical shells is just given by this function here, y equals x squared plus 1. That's what's going to determine the height of each of these shells as you sort of go and collect them up. That's y equals x squared plus 1. So the height is just x squared plus 1. And so simplifying this, that's just x cubed plus x. Integrating that will give x to the 4th over 4 plus x squared over 2. And that is the process of integration, so no more dx or evaluation or integral sign, just an evaluation symbol. X equals 0 and x equals 1. Plugging in 1, that's going to be 1/4 plus 1/2. So 1/4 plus 2/4, which is going to be 3/4. Minus 2 pi times, that's going to be 0. So it turns out to be 3/4 times 2 pi, or 3/2 pi, which was the result that we got previously. On Tuesday. But instead of having to split this up into two integrals, one which gives an area of pi and the other one which gives an area of 1/2 pi, this is all one integral, and it's not even, that difficult of an integral in addition to that. Okay, right, that's pi. Yeah, one integral. Yeah. Yeah, this was the right, this was using the washer method. That's right. Anyways, yeah. All right.
I have a question.
Yes.
For how do you find p of x as x?
P of x?
Yeah, like in the integral.
Oh, so I will say it will usually just be x or y. But what you can do is think about just the series of shells that are going to happen. So we have this approximate shape. If we just think about one of these shells, imagine taking like any arbitrary slice from within the region and just sort of, okay, so first of all, think of the integral as, because of these bounds, starting at 0 and going to 1. And it starts over here. It makes, the first little, tiny little slice, and it spins around the axis and forms a very narrow tube. As you move along, those tubes get slightly wider. And I know this is a mess. So you're here, you get a slightly wider one when you go this way until you're all the way at where you end, and you're at x equals 1, and you form like the widest, shell. And then you stop because the integral only goes from 0 to 1. But throughout that whole process, the radius of those cylinders is just where you are on the x-axis. So just whatever the value of x is, as it goes from 0 to 1, at some point it'll be 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. It's not a constant radius. It is growing as you move from 0 to 1. But through that whole process, that radius just is whatever the value of x happens to be at the time. So at minimum it's 0, and at maximum it's 1. Yeah, but because it is. The radius of these cylinders does change as you go from 0 to 1, but at the same time, it changes, but it just is the value of x. Right, so there's that. Here's one dy. And this is being revolved around the x-axis, so that if you do this dy, it also ends up becoming the shell method. But the shape that's going to be generated is essentially just this sort of cone. Okay. So this is being done dy. So the volume is going to be represented by 2 pi times the integral from a y value to another y value. Oops, not y equals 0. We don't know what it is yet. Of p of y, the radius in terms of y, the height of stop doing that. The height of the cylinder in terms of y dy. Okay. So if we just sort of take if we just sort of try to draw a little representative cylinder, or a representative cylindrical shell. Okay, so y clearly so the bounds of integration, right, are going to be y values. And so y is going to start at -6, actually, because it's always going to go from low to high. So y equals -6 up to y equals 0. And if we think about the radius in those terms, okay, so we're starting at y equals -6 and taking slices, going all the way from -6 up to y equals 0. At this place where we start, when y equals -6, the radius, how far that the edge of that shell is from the axis of rotation, is actually 6, right? Because these radiuses are always positive. So it actually turns out that the radius function is -y as opposed to just y. But if you forget the negative, all that's going to happen is that you would get a negative volume, which you would know then to just flip into a positive. Like, it would still have the same magnitude, so it's not, the most horrible thing if you just forget, that the negative is there. Okay. So y starts at -6 and goes to 0, and as that happens, the radius goes from a radius of 6 to a radius of 0. And the only way to make that happen is to have the radius function as -y. It's the negative of whatever y value you're at right now. And that has to do with the fact that this shape is below its axis of rotation. All the ones we've seen so far, the shape has been above its axis of rotation. Now, what describes the height of these cylindrical shells? You sort of look at these shells, or if you look at these slices, you might notice that this is a case in which we have sort of a top minus bottom, or right curve minus left curve kind of situation, because the curve that forms the top, of this little slice is the curve x equals 8, and the curve that forms the bottom of this slice is x equals instrument. I forgot to mention, since this is an integral dy, you want all your functions to be x equals a function of y. Okay, so all right, so this rightmost curve is x equals 8. This leftmost curve is x equals 2 minus y. Okay, so we're doing shells, top minus bottom, or rightmost minus leftmost, is going to form the height of this shell. So that's 8 minus 2 minus y. So the height of the shell is slightly more complex because it requires you to take these two curves and subtract them. Subtract the take the rightmost one to be the first one, and then subtract the leftmost one. The difference between them is the height of that shell. Yeah. But in the end, it does just end up being a polynomial function again. So 2 pi times the integral from -6 to 0 of, I guess we'll just sort of take this slow. 8 minus 2, so that's 6. 8 minus negative y, that's, 8 minus 2 is, 6. And then minus negative y is plus y inside the parentheses here. Which, after you distribute the negative y, negative 6y minus y squared dy. Okay, and if you integrate that, that's going to be negative 6y squared over 2. So that negative 6 over 2, that's going to simplify into negative 3. So 2 pi times negative 3 y squared minus, and then the y squared is going to integrate into y cubed over 3. And it's going to be evaluated at negative 6 and at 0. So the first we'll plug in 0. Negative 3 times 0 squared minus 0 cubed over 3 minus, and then we'll plug in negative 6. 2 pi times negative 3 times negative 6 squared minus negative 6 cubed over 3. Okay, and if I did everything correctly, this should end up being a positive number, hopefully. So this first part is just 0 minus 2 pi times negative 6 squared is 36 times negative 3 is negative 108 in here, and negative 6 cubed is negative 216, but that's subtracted, so it's plus 216 over 3. So through this sort of convoluted series of signs, let's see if I wrote 324 thirds. Okay, so negative 324 thirds plus 216 thirds. That is, well, that's negative 108 thirds. There's an extra negative on the outside. So it's positive 108 thirds times 2 pi. So positive 216 thirds pi. is the volume of this shape. I'm sure there were easier ways to go about evaluating these numbers, but you know, at this stage, it's just plugging in a number. It's, you know, the evaluation of an expression. So you know, if you get here but you make a mistake at this stage, actually don't have any advice except for be more careful. So there's not really much I can say about that. Yes.
You're gonna allow like basic calculators so we can do this stuff?
Yeah.
Without,
Yeah.
making mistakes?
I guess you'll want to leave the pi off until the very end, but like all the integers and rational numbers, yeah, like you can definitely, yeah.
That is divisible with 72.
Damn, you're right. Yeah, because it's 6 cubed, so of course it's divisible. You know, it's the cube of 6, so of course it's divisible by 3. Okay, that's 72 pi. Okay. Yeah, cool. And then one last one. Blah, blah, blah. Yeah. Okay. I'll set this one up, but just not evaluate it. Just to show you like how the radius function sort of works in these particular cases. Okay. So here's the graph. Y equals square root of x, that sort of goes like this. This goes until x equals 1, so... And there's y equals 0. So it's this shape. And you're revolving around the line 1, 2, 3, 4, 5, 6. Okay. And I know this is kind of a mess, but you're revolving it around this line. So quite far away from the shape, actually. And it's sort of, it's going to make this weird ring. You know, it's going to have a straight walled ring on the inside, but it's going to be curved on the outside. The way that you do this is you'd integrate this from, sorry, and you'd be doing this dx so that it shells, because that's the easier way to do it rather than dy. But x goes from 0 to 1, like that's like the literal region, like the actual shape. 2 pi in front. The radius of x is going to be 6 minus x. Is that right? This goes from 0. Yes, okay. And the height of x is just going to be the same, you know, the usual thing. Now the reason it's 6 minus x is because your axis is at x equals 6. So if you remember, x goes from 0 to 1. So if you imagine starting off at 0, how far are you away from the axis? 6 units, right? And as you slowly move through the region and you get to x equals 1, at that point you are 5 units away from the axis. So your radius goes from 6, and you know, as you get closer to the axis, it goes to 5. That's the reason for this. You can see that if you plug in 0, like, you know, if you imagine you're at where you're starting out and you plug in 0, that gives you 6 for the radius. And, you know, as you go towards, you know, x equals 1 to where you sort of finish off the region, if you then imagine being at x equals 1, you can plug in 1 there and get your radius of 5. So that's what happens. You know, that's the only thing that's different about if you have a radius like, a axis of rotation like x equals 6 instead of the y-axis is, you know, just instead of a simple x for your radius function, it might be 6 minus x. That's the only thing that changes when you have this sort of other axis of rotation.